from Spark. Thank you.
Thanks for the introduction. Hi, my name is Matthew. I work at Salesforce. I see a lot of familiar faces here. Thanks for coming to my talk. So I would like to thank all of you for coming over and actually thank the organizers. It's such an amazing, really amazing conference. Delighted to be presenting here. So I do machine learning. I do Scala and Spark at Salesforce. And this is a little bit of a niche talk. We'll be focusing on how to make your models portable. But if you have questions around type safety, Spark and stuff, you can talk to me after. So where do we start? Let's start a little bit with a machine learning pipeline. So this is pretty much typical machine learning flow that you would see from the books. And then you can layer it out in kind of 6 stages, more or less, where you have your data produced by some process. And then you run some feature extraction, from which you extract the valuable pieces from your data. You do some kind of feature engineering of imputations and maybe useful statistics for your data. You do feature selection on top. And this is pretty much the 3 pieces where you do the ETL. Right? So this is where we do the kind of more classical ETL part of our data pipeline, or machine learning pipeline in this case. And then there is a learning phase. In the learning phase where we want to compete head-to-head different machine learning algorithms one to another. We want to take logistic regression, random forest with our XGBoost, whatever comes next, TensorFlow models. We want to compete them. And we want to do some evaluation on those models. And eventually, we want to produce some useful scores and insights. So this kind of represents the result of this pipeline. This is one best model that we then eventually want to serve. So this gets us to the scoring flow. In the scoring flow, it's not much different, except that we don't now compete models against each other. We already know the best model. We've learned from a training set, multiple training sets, what the parameters are. And now we have to repeat the same ETL process because we need to keep the dimensionality of our data the same and apply the model. Right, the same score calibration repeats, insights, and so forth. So this is kind of give us the baseline for this talk, what the machine learning pipeline is. And then we produce scores and insights here. The thing is that best model spans across those steps. It's not like something just the algorithm part. We actually learn a bunch of stuff during the ETL part as well. So whenever we aggregate, we actually might learn some of the properties of the data, which we then use for our best models. For example, we started by inspecting some of the text data, but we figure out that it's not a regular text data. It's just a categorical data, just like a limited set of values. And then we can actually treat them better as a categorical types instead of tokenizing them and applying different text mining techniques, which will be less efficient in this case. So model actually, again, expands outside just the algorithm part. It goes to the ETL part as well. So how do we encapsulate it? In Spark, it's very natural to think about it as a single application. It's not necessarily the case whenever you deploy it in real life, right? We might have different process that actually does some of the feature engineering for us offline, but you can think about it as a single application, something that you can kind of run it and think about as a single unit on your laptop or on a cluster. And a lot of people do that, and I mean, it's kind of a very typical scenario. It's not necessarily good or bad. Again, it suits whatever suits your use case. What happens in Spark, right, is that we have a bunch of stages that we stitch together in these pipelines. And those stages might look familiar. So I just kind of minimize the names so they can fit into the same graph, but they have much longer names in Java classes and in Python also. Where in this case, just put some examples of, OK, we want to compute some feature distributions on our data. And then we want to decide now, should we tokenize the text? Because we decide it's text data. We want to tokenize it, or we want to pivot it. So this is a decision that we will have to learn during the learning phase of our model. And then we want to encapsulate it into the pipeline whenever we save it and then serve it. So this is one of those learning parameters that we want to keep around. So whenever we train a model, again, going back to the example of trained, right? We now learned all those, like I put those green things, so those are things that we learned when we trained the model, is that for the imputation, for example, we learned what's the mean on our training set. And then now we're going to be imputing this value for the missing, instead of the missing values on our scoring data set. Same goes with the tokenizer, for example. Maybe we learned what the most typical languages are, and then we learned maybe some stop words that we want to exclude immediately from the scoring data. So all these things have to be included into the model and then served. So I actually like to think about this whole thing as more of a, again, like a functional twist a little bit, right? So we have a program that we write, and then we train it on a data set. So we apply it on a data set, which then produces another program that we can now apply on a new data set. And we can think about it as a function, right? It's like a train function as a function that will produce a scoring function that will be applied on a data set of the same type, which then will produce a data set of type S. So I wish Spark engineers would think about that. Well, anyway, maybe they thought, but the reality is like we actually live in a much less beautiful world. So Spark is actually pretty messy to work with. So if we can somehow to get to that purity, that would be great. Maybe like in several more iterations, we'll get there. Interfaces grow based on the usage and like the feedback. So I guess it's in our hands to get there. So what's really the problem here? We would like to train a model on Spark. So that's the first thing. If you're not crossing that part, probably, or you don't have enough data, or you actually have to be very careful in that moment. Do you really need Spark? So if you decided that you need Spark, the rest of the talk is for you. If you don't, and a lot of answers are no, you don't really need Spark. Again, there's people that really like to ride on this buzz of yeah, the big data and stuff, but a lot of things you can really, really solve without it. So if you decided that your company or team needs Spark, then eventually what you'll have to do, you'll have to save your model somehow. You have to train it on the data set of multiple models and then juggle it to the production serving system. So we need to load the model and then serve it efficiently depending on your runtime, you'll be running it on Spark. This is, again, very natural because it's something that's very easy to do out of the box. Or you want to run it on some other runtime. So examples might be you want to, serve it on some application server in JVM where request comes in and you immediately score it and return back. So yeah, why not serve it with Spark, right? Spark has a messy graph of dependencies, and it's, for a long time it's been stuck with an older Scala version. It really only runs on Java 8. That's like a long list. JSON4S problems, and there's just a ton of things, and it happens with a lot of legacy code bases. So it's not unique. We see the same problems with other large systems such as Hadoop, which are much more modular now, but before it was the same thing. So I guess it will take a time for the ecosystem to evolve. But so far, I see a ton of projects where people actually need this kind of stuff. And then in the real-time part, OK, so what I wrote here is like a real-time scoring. So you can do real-time scoring with Spark. It's just not, you cannot really do it in a sub-millisecond of very few millisecond latency for the record. Data frames have overhead, reasonable overhead, like a significant overhead for the runtime, and you will see it once you start working with it. So what are the prerequisites here, right? We want to produce a model that is realizable and, of course, deserializable. We want to make a model to be interpretable in some runtime. And we also want to assume some things, right? So for sub-millisecond latencies, actually, most likely you won't be doing most of the joins and aggregations. You can still do some simple joins, but like one-to-many, many-to-many joins, those are like cross products. Sometimes you actually do need cross products. They has to be done in the training phase. right? You don't do them at your scoring time. The execution of the model has to be thread safe, and then as I mentioned, Spark is probably a no-go. So this little scale on the bottom, I put that. So like, how far can we go from Spark? So we can go from, OK, we have a Spark runtime, or we can have Spark runtime to just load the model, and then we completely abandon it and we score using whatever, JVM probably in this case, where we can just use some of the Spark dependencies for some of the reasonable functionality, or we can just do JVM with something else. If you're not in that camp, you can try to go further, and I will now explain how can you do that. But first let's see how Spark deals with serialization of models. So Spark defines this interface. I took one of the examples, IDF model, that you have to extend ML writable trait, in which you have to produce an ML writer in your write method. ML writer will have a safe implementation, pretty much have doesn't have much limitations to it. It just requires you to provide it provides you with a path, and then you have to figure out what to do with it. You also have a Spark context there. Most of the models that you have on Spark, they actually do I have the example? Yeah. So most of the models that they have in Spark, they just use Spark session, and then they store it using Parquet files. So not all of them. Some of them are, some of them not. So you find out once you start using them. When I speak also here is the model, right? So every single stage in Spark is a model on its own. So whenever you stitch them in a pipeline, you actually have a bunch of those little models saved on your path. So this is really not great. And then the load, very close, right? Your model have to provide a reader, and then you have to provide the reader function. So this whole code, it lives in Spark. Every single stage you write in Spark, you have to write this stuff. And if you extend or you write your custom stages, you also have to deal with this. But how do we get to the serving part? So serving part is this, right? After you load it, in Spark currently what you can do, you have this transform method for each method. And on Spark pipeline, what it does, it takes your data frame and then applies all your stages one by one sequentially on a data set. Completely unconstrained interface. You can pretty much do whatever you want in there, but most of them look like this. They either apply UDF, and you will find very quickly that this is very slow. So all those data frames optimizations, they work fine with columnar, simplified columnar operations. They don't work with UDFs. And then whenever your pipeline is more than 3 to 5 stages, depending on the data size, you already see the impact. So this is pretty serious stuff. So which makes it totally unusable for real-time use cases. So again, to recap, out of the box, we can save and load to Parquet files, and then we can use Spark runtime to transform data over data sets. So what are the options we can actually, where can we go from here? So there is an abandoned part of Spark. It's called mlib local. This is like a little library that has an implementation of a local linear algebra. It doesn't support Spark models yet. And there is several year-long discussions about how to improve it, but really nobody touched it. So I guess if you guys want to contribute to open source, that might be a good way of doing it. I don't think I have enough time to do that yet. So, but maybe. So there are some I put some Spark JIRAs here to track. So there are some ideas actually how to move this forward and maybe reuse some of the community contributions. But so far, nothing. So another thing is the Databricks local offering. So you might also have seen their announcements of that you can export Databricks models from a notebook. And I've seen some data scientists using this. This works OK. There are some missing parts. But there is no source code, so you have to take a jar from Maven and decompile it, and so they're not even supporting it. So again, hopefully it will become ML local eventually. Another two things I want to highlight is that the different approach where a group of companies including IBM, they decide, okay, we have to build a standard, and most of you already know about Pmml. It's like was a de facto standard at some point. Now it's less and less popular because of its limitations. So first of all, XML and XSL, I mean, they have strong benefits, of course, being typed and everything, but they're really, really painful to work with. It doesn't have control structures either. So if those like forks that I mentioned, where you want to, should I pivot or should I tokenize, you cannot really do at runtime during scoring. So here goes PFA. So PFA, comes PFA, and then this kind of improves on the Pmml offering by providing a bunch of conditional operators and variables. And I found it actually very nice, especially because it's a standard too. So first things first, you have a very strong foundation of rules, and then we have actually several runtimes that we can use. And recently, they announced there was an Spark library for Spark, which supports most of the Spark models. I mean, it's still very early, but usable. So, and then of course you can use some other third-party offerings such as Mleap from CombustML, where you can bundle your pipeline into their format and then run it. Another option is, of course, write your own runtime, in which you would use Spark to read and write, right? And then you would use some kind of custom runtime. You would write your custom runtime for the Spark pipeline. And here I want to just do a brief case study on the Transmogrified library that I'm developing. So this is automated machine learning for Spark, and we took an approach of actually building a custom runtime. For us, it was important to have a sub-millisecond latency, but we didn't mind that if it's on Spark we didn't mind that it runs on JVM and has Spark dependencies, since we already have them. So what we did, we actually implemented some base classes to marshal the stages using the Spark writers. And then we added a new function to transform any arbitrary key value pairs. So we wrapped all Spark models in our classes, and then internally we used the Java reflection method mirror API, which is surprisingly fast. I mean, people like to think about reflection that it's very slow and not performant. The thing is that reflecting method is slow, but once you reflected it, execution of the method is really fast. So you can reflect it, keep it as a lazy val or val, and then execute it on per cell level, extremely fast. So it's just really only probably twice as slow as a regular direct method invocation. And this is how it looks like. So you can have a model that wraps around Spark model. We reflect a bunch of internal methods. And here you go, have a type signature to do the same transformation that Spark model has. But now the difference is that we can use this transform function to execute it on just pure JVM without need of data frames. So whatever is not wrapped, we just use PFA. We just use PFA engine to execute it, and I just built a little performance. Like I ran a little benchmark here. I executed on the 6 million rows, and it averaged about 0.03 milliseconds per record, which is like 2 factors of orders of magnitude faster than what you get on Spark, or sometimes 3. So what have we learned, right? So Spark PFA very still, well, I didn't mention that, but they have some buggy stuff still. You know, it's pretty much the one-man show yet. So expect some bumpy ride on this. Would be cool if there was a Scala to PFA, whether a compiler plugin or a macro. I believe it should be a compiler plugin, because that would actually increase the adoption of PFA overall, and would be much easier for people to use. And then, yeah, custom code libraries, I would prefer to have a standard again. So going back to the standard part, I would love to have a standard that several teams, several companies work together, and we don't reinvent this wheel of custom runtimes and try to do things like that. So I want to end with this little joke. So does anyone recognize what this is? So this is JSON. Cool. It's very simple. OK, now, how many libraries do we have to parse JSON? So yeah, GitHub says 4,400 just on the GitHub. And then Google says I can even find them near me. So it either doesn't parse my query well, which is it most likely doesn't. It literally says that I can find them. So instead of a summary for you, it's like a little decision diagram. If you're in deep learning, which I didn't put on the presentation because it's only 20 minutes, and I have 15 seconds left, you go with a standard called ONNX. Check it out. Again, several companies actually gathered and trying to build a standard. If you don't mind Spark, just, yeah, like whatever. Look at it. Make your decisions based on that. One more thing. If you still want to run Spark, that's another thing I found a couple weeks ago. So Microsoft open sourced their Pmml Spark library, and they have Spark serving. What this thing does, it actually allows you to bypass Spark driver and a data frame and hit directly to the executors. I mean, you need to wire this whole thing, but this kind of eventually bypasses Spark and allows you to use the Spark parallelism. So if you're up to a challenge, you can also try that one out. So questions? Yes?
Did you consider at all to keep using Spark for transformation and data preparation purposes only and build models somewhere else? And if you did, why did you choose to go with Spark anyway?
So yeah, I exactly mentioned this. Like, why would you even stay with Spark, right? There is still some ETL you want to do before scoring. So actually,
no, I'm saying like the only model fitting stage.
Uh-huh.
So why you?
Oh, why we? Yes, of course. There's a ton of ETL. Yeah. There is a ton of ETL that you have to do. That's like, it's actually, this is the cool part of Spark, where you can leverage the parallelism and the aggregators across all those executors. Yeah.
But then you can store
the
results and
exactly.
Somewhere like scikit-learn or Python.
You could, yes.
Are there any more questions for Matthew?
And what are we missing from
Mleap? So Mleap is so it's actually pretty nice, right? But it's just fully file-based and back from the file. And it's custom. It's keep changing. We have seen some breakage across versions. So I don't think this should be it should be less of an issue for standards. Those develop slower.
If there are no more questions,
OK.
let's thank Matthew.
Thank you very much.